next talk is given by Eric Hogg from Yale University, and Eric will tell us about converting data parallelism to task parallelism and runs.
Thank you. So this is joint work with a lot of the same authors that were on the last paper. Yoel, who couldn't be here because his second child was just born, so he's home with them. So congratulations to him, but then also Michael Vollmer, and then myself, Trevor McDonald, and then Ryan Newton. So anyway, let's get into sort of what we're trying to do here. If you look at modern computers and the way that they've sort of been evolving over time, this is probably obvious to most of us, but we've all got a lot of cores on our CPU right now, and there's sort of even more of them coming. It's not uncommon to see 8 or even 48 cores in the same machine now. And then you also typically will have a GPU with them as well. And not only that, you'll have sometimes a second GPU. And these GPUs aren't always the same. So like this laptop, for example, has got 2 GPUs in it, one for sort of low power run-of-the-mill stuff, and then one for high performance gaming and all that. And so we get this big diversity of hardware on our computers nowadays. And so the question is then, how can we take advantage of all of this? There's been a lot of work in DSLs for taking advantage of maybe just the CPU or just the GPU or just this one aspect of it. But what we're looking at now is trying to take a single program and make use of all the parallelism that we have available. So we're specifically in this work focusing on the case of where you have 2 basically identical GPUs, but we believe our techniques will generalize pretty easily to a lot of these other configurations that I just listed there. So we're starting with the accelerate language, which is a data parallel DSL embedded in Haskell for doing array programming. It makes it really easy to express high-level parallel computations using these array combinators like map and fold, and then the compiler is pretty good at generating fast code for that. So here's an example of what an accelerate program looks like. This calculates dot product, and so it takes 2 vectors of numbers, and then it gives you back a single scalar. And you can see inside of it, it looks basically just like regular old Haskell. So we do, in the inside there, we do zip width. So we do the element-wise product of 2 vectors, and then we do fold to sum them all up together and get the result back. And naively, accelerate would generate 2 kernels for this. It would one to do the zip width and then one to do the fold, and so you'd have 2 different big bulk operations on the GPU. But then there's also been a lot of work done to combine these all together, so to do really aggressive fusion and sort of collapse multiple kernels into a single one that can avoid temporaries and make better utilization of the GPU. But what we're doing is sort of the opposite then. So once you fuse it all together, we're going to do fissioning. So we combine a bunch of kernels together and then we split them up again. And I think this is sort of hinting at this interesting space of rewriting, expanding, and collapsing programs in a way of massaging them to fit into the hardware that we have a little bit better. So what I mean by fissioning is, here's sort of the most straightforward example. We have this vector up at the top of x1 through x8, and then we run this through map, and then you get f of x1 through f of x8 out in the result. And then since GPUs are great at doing massively parallel computations, this just runs in parallel, and it all works. So fissioning then is we take this map and we split it into 2. So we've replaced that single node there with a split node that takes the array and splits it in half, like that. And then we run map on both of those halves and then combine the 2 back together. So there's our 2 intermediate results, and then we do a concatenation to combine them back together. And so the nice thing about this is that we can basically have these rewrite rules that are correctness preserving. We just pull out a map operator and stick in this more complicated operator that still preserves the same meaning, at least for the program. And now what we have is twice as much parallelism, or at least 2 independent parallel operations that we can schedule onto different devices. So I mentioned that this is different rules for fissioning, and so the one that I just showed you there was map. So map of f over some array expression is we split that up into 2 subarrays, and then we map over both of those and concatenate them back together. And this pattern of splitting and then applying the operation of the 2 halves and then combining works for a lot of different operators. So another one that accelerate has is zip width. And again, it works the same way. Now we have 2 inputs instead of just 1, but we split both of the inputs. We do a zip width over the 2 of those, and then we combine the result back together, and it just works. And so we can generalize this to a bunch of other operators in Haskell, or in Accelerate anyway. So we can do folds, maps, generate, replicate, zip width, back permute, and use. And they all take slightly different forms, but it's this general theme of splitting up your inputs, running the operation on 2 of them, or on the pieces of it, and then combining the results back together. A couple of them ended up being sort of tricky and subtle, though, and so I'm gonna point those out in a little bit more detail. So one of those is fold, and you'll notice that there's no concat in that rule over there. So we split it up into a zip width, and it'll be really obvious in a second why that happens. And then another one that ended up being very tricky was replicate. And so what replicate is used for is to sort of extend an array into multiple dimensions. So if you have a one-dimensional vector and you replicate it along some axis, then you turn it into a 2-dimensional vector. Or you can take 2-dimensional arrays and replicate those into 3-dimensional. So you just sort of extrude along some dimension. And that ends up being sort of tricky with this splitting, as we'll see in a little bit. So fold, if we just did sort of what we did before and just blindly stuck in a concat because we thought that would work, what ends up happening is you split up your array, of course, and then you end up with 2 scalar values that are the fold applied to the left and right halves of the array. And then if we concatenate them back together, what we get is we get a 2-element array, each having half of the results, and that's obviously not what we want. We want a single element back that has both of them. And so what we do is just replace that with zip width, and then zip width sort of completes the operation, and we get the result back that we wanted. Replicate's a little bit trickier, and when I first started working with Accelerate, it took me a while to wrap my head around this particular operator. But so replicate takes this shape expression that tells you how to change the dimensions of it. And so for a one-dimensional vector, we can either extrude it row-wise or column-wise. And so on here I have graphically shown the 2 ways of doing that. And so let's just consider this version of it. If we split it up, that's pretty straightforward. You split it into 2 different arrays. And then you go and you replicate the 2 halves of it. So now we have 2 different ones that we've extruded along this dimension. But then if we were to go on and concatenate those 2 together, there's this problem of which dimension do we concatenate them on? Do we concatenate the rows together or the columns together? And so we could say, oh, well, let's just concatenate on the 0th dimension because that's the one that we split on. So let's concatenate columns together, I guess. And you'll see sort of, obviously, that's wrong. That's not a rectangle anymore. And that's something that we need. So we have to be careful then. What's happened is we've inserted another dimension into this data structure. And so we need to account for that. And so the right thing to do is to stick the other piece onto or basically concatenate the rows together rather than the columns. And so concatenate over the first dimension, and in our rule what we do is we have this function called new index, which you can see under the concat, which takes the new shape of the object and then the dimension that we did the split over, and then figures out the right thing to do for all of that. So as pointed out, there's some correctness concerns with this, or it can be kind of tricky to get these right. We have this library of rules, but we want to make sure that they work. And so we spent some time doing a model of these rules in PLT Redux. And what that let us do is that gave us this smaller test bed to try out lots of different rules really quickly and find the ones that work, and also sort of see graphically where things went wrong and how we can patch it up and fix it. And so we basically made a model of the Accelerate language, and then started working in these fission rules. And I'm not going to go into a ton of detail into it in the talk, but you can read more about it in the paper. And the cool thing about PLT Redux is it lets us get these examples like this. So these rules are non-deterministic. There's often multiple rules that can apply, and you can apply them over and over and over again. And so that gives you lots of different strategies for how to split apart a program and then collapse it back together. And that's shown graphically here. We start with a single expression over there on the left, and then can go through all these different execution paths and but the important thing is that they all end up at the same location. So we didn't go so far as to do a formal proof of correctness for all of these, but we did very extensive testing in PLC Redux with lots of different test cases, making sure we got good coverage over all of the operators that we knew how to fission. And so that helps increase our confidence that what we're doing is not going to break user programs. So I'm going to talk a little bit now about the implementation, and then I'll get into some about the scheduling and just to sort of touch on this, and these are things that we go into more detail in the paper. So I mentioned one of the challenges is that we have non-deterministic rules. There's lots of rules that apply at any given time, and it's not always really clear what the right thing to do is. And so we just chose a very simple heuristic on this. We just basically we walk over the syntax tree, and any operator that can be fissioned, we just fission it, and we fission it once and leave it at that. This might be a case where the auto-tuning monad, like we saw in the last talk, could help with this too, is we can decide which rules we want to apply at a given time. But for now, we're just doing something pretty simple. And there's basically two goals, and these are good goals really for any language implementer. We want it to be correct, of course, and then we want it to be efficient. And so the correctness we get in part from the PLC Redux rules that I talked about earlier, but then also we get correctness through the Haskell type system. And one of the, I think, cool things about the way Accelerate is implemented, although it's frustrating when you're trying to change the compiler, is that the shapes of all the arrays are encoded in the type system. And doing these rewrite rules requires us also to prove to the compiler that we're maintaining a lot of correctness and variance in the code. And so that prevents a lot of errors. And then for efficiency, we get that again through a lot of tricks that the Accelerate compiler is already doing. For example, it has this notion of delayed and manifest arrays, where a manifest array is one that takes actual space up in memory, and then a delayed array is more like a computation that you might want to inline into some other one. And so it's able to, so one example is we've got all these splits and then concats that, we could imagine like concatenating an array and immediately splitting it apart, but these delayed arrays and the Accelerate internal representation allows us to just sort of get rid of those. And if you have a split that goes directly into, or a concat that goes directly into a split, you just eliminate that, and it helps us keep our performance high. And then so scheduling, I'll just say a tiny bit about that as well. The Accelerate ends up making, its syntax tree ends up looking sort of something like this. So you have this like chain of lets, and here we sort of impose some nesting structure on there that just sort of shows how this basically comes from the fissioning. As you have a let and then you fission, and so you've got two like sub expressions on there too. And so from this, we're basically able to recover a task graph. So for that expression there, you would end up with something that looks kind of like this. And you can see that our expressions A1 and A2 and A3 are all independent, and so we can freely schedule those. And so our compiler, or our runtime system, just basically looks at what work is available to do, what devices are available, and schedules them onto it. And then it does take into account, it tries to account for data movement costs as well. So if the data that you need is already on a particular device, it will try to schedule that computation on that device to avoid unnecessary copies. But this is, again, an area where there's a rich literature around scheduling, and we could probably do some really smart things in this. And then, so let's talk about evaluation. Does this actually work? Can we get performance out of this? We'll have a couple of different benchmarks to look at. The first one is this in-body simulation. And so this is showing the number of bodies that we're simulating, so it's gravitational in-body. And then the y-axis there is the median time to run this in seconds. So lower is better. We're showing execution time here. The top curve there is basically, so we have the top curve there, we've got the Accelerate, which you can't really see it, so just plain old Accelerate, and then we also have 2 GPUs with fissioning off, and so that's, if you're using 2 GPUs and not fissioning, of course it's not really going to change your performance. And then we have 2 GPUs with fissioning on, which is the orange line at the bottom, and that shows us getting about a 2x performance increase, so that's good, that's what you would expect. The one that's really interesting in this one is the green line there, which is running the fissioning process, but we're only actually using 1 GPU. and we still get a performance improvement on that. So we think the reason for that is that basically the amount of data here, it's an n-squared algorithm, so there's a lot of computation for not all that much data. And when we split it up like this, we actually are sort of accidentally titling our program for better cache usage. So that's kind of cool that we can get that speed up even with a single GPU. The next one we look at is matrix multiplication. And this one shows here, if you fission on a single GPU, it gets worse, which is sort of what you would expect because you have extra overhead in doing all of that. But we do get, when we have 2 GPUs and fissioning on, we get a slight performance improvement, although not quite as good as before. But still an improvement, which is good. And then there's one case where we don't do as well, and this is Mandelbrot set. And so the fastest one there is the red line at the bottom. That's just the plain old vanilla accelerate. And then all of the different ways of fissioning with or fissioning on or off with multiple or single GPUs still leads to about the same performance decrease. And so the question is sort of, why is this happening? What's going on here? And if you look at the Mandelbrot set, it sort of becomes really obvious. So if you've written Mandelbrot before, you know these black points in the beginning or in the middle are the ones that take a long time to compute, because that's you basically iterate until you escape, and then the black ones are the ones that never escape, so you just sort of go up to some limit and then give up. And so you'll notice that we just sort of arbitrarily picked a dimension to split the iteration space in half on, and this ended up with one half having a whole lot of black pixels in it and the other half having very few of them. And so we have unbalanced workload here, which means that a lot of the overhead, someone's going like this, and that's, this is a case where if we just split on the other dimension, we probably would have gotten the double speed up like we wanted. But again, this shows there's sort of some subtlety in how we decide to split everything up and all of that. But, or even if we just do one more level of splitting, like we split vertically and then horizontally, that might have helped out too. But anyway, the technique shows promise, and we get performance in a lot of cases, and then in others, there's clear ways to improve it as well. So with that, I just want to leave you with the thought that we're showing that fissioning, as these correctness-preserving rewrite rules, are a way of exposing additional parallelism to be able to take advice of more computational devices in your system. With that, I will say thank you. Yes.
So, you mentioned how one of the things you guys want to look at, maybe through auto tuning or something, is to figure out the right way to do fissioning. And you gave a nice example at the very end that clearly one of the primary concerns is going to be things like load balance, making sure that the chunks of work that you create have roughly the same amount of work, or in some way good. What are other concerns that you would have to worry about given the DSL that you have, given the kinds of things you're trying to do? What other stuff beyond load balance will matter?
So the question was, we talked about how there's a big space here to explore, and there's a lot of concerns. For example, load balance is one of them. And then what are some other concerns that we would want to take advantage of or to keep in mind? I think sort of the size of the work that you have is a good one too. Certain devices are better suited for certain granularities of work. For example, there is the memory hierarchy has a lot to do with this as well. So we saw some caching effects in there too. There's also the PCI Express bus is just horribly slow compared to the other buses that are on the system too. And so we want to avoid doing that. It may be that there's certain programs that are structured in a way that works really well on the CPU but not so well on the GPU, and you may want to balance your workload differently on that. So those are some that come to mind right away anyway. Yes?
So it looks like you're just looking at the computational aspect of this whole procedure. And have you considered like transaction cost of moving stuff to the GPU memory and back?
So the question was that we're mostly focusing on the computation cost here, but have we considered the transaction cost of moving data over to the GPU, doing the computation, and moving it back? We do some of that now, actually. So our scheduler is sort of aware of where data has ended up, and it will try to avoid putting in needless copies in there for one. But yeah, that's something we do need to consider more, is For one example I always use is doing a dot product on the GPU, and just because the PCI bus is so slow, it's unless your data happens to be on the GPU, there's never any reason to do a dot product on the GPU. So that's something that I think a smarter scheduler would be able to look at that ahead of time and try to optimize where to place all these things and avoid transaction costs. Yeah, in the back.
When you showed us the Redux reduction graph and everything was merging back into a single point, was that from an eval step, or are all of the fission rewrite rules converging together?
Okay. So the question was on this graph that I've got up here of the evaluation in the PLC Redux graph. Is that because the fissioning rules all eventually converge on the same point, or is this also showing evaluation and reduction? And so our PLC Redux model sort of freely mixes fissioning and evaluation in there. So what you'll have in here is a step of like fissioning, and then you might take an evaluation step, which exposes some more fissioning, and so it'll fission. So it's sort of it does strictly more fissioning than our implementation, the compiler that we have does, but it's sort of a superset of what the compiler does. So yeah, fissioning is sort of where you see the branching go out, and then there's also sort of non-deterministic evaluation rules and so on, but the thing that brings us back together is the evaluation steps.
This is maybe something that a sufficiently clever runtime system might try to do?
Perhaps. Yeah, you could imagine sort of dynamic, especially because Accelerate has got the syntax tree when it's running, you could imagine sort of trying to dynamically split up further depending on runtime information. Let's see that. Yes?
So I would really like to use this. So how would the user interface look like? So can I usually, as a user of Accelerate, specify how to split these out? Or for example, can I specify just splitting for the result of the computation and then the other intermediate arrays are split in that form?
Okay, so I think if I understand your question right, it's like what does this look like for the user? How much do you have to specify to take advantage of this?
Or is it automatic? Or is it fully automatic?
It's totally automatic. You just take an unmodified Accelerate program and run it through the system, and it goes through and splits it all up, and will take advantage of multiple devices without any changes on your part.
But the user knows something about their GPUs, and he would like to have some control.
Yeah, so I guess the user does know something about their GPUs and the hardware layout, and I think maybe one way you could see that happen is you give Accelerate a configuration file that says what the device looks like or something like that. But
We can control that through the configuration file.
So a possibility is to control it through a configuration file or maybe runtime parameters that you can set from your program, or that's something we haven't really done a whole lot with now, but for the most part, it should just be totally transparent and automatic to the user.
So does this happen after fusion occurs, or does it happen before fusion?
So the question is, does this happen after fusion or before fusion? And it happens after fusion. So the fusion pass runs and sort of combines everything as much as, I think of it as sort of a vertical versus horizontal split. So you have kernels that feed into one another that it collapses into one, and then we split sort of horizontally to get pieces that you can run on different devices. And then it's careful with its code generation to try to avoid creating new places where you'd want to do fusion, but you can't.
Are you splitting in half always, or can you balance the rules?
For right now, it always splits. So the question is, are we splitting in half always, or can we change it? And right now, we're always splitting in half, but we've played around a little bit with doing an unbalanced split. So this matters a lot when you're doing a CPU-GPU version of it. Your GPU's got way more floating point throughput, and so you want to put a bigger amount of work on that device.
Maybe one more question. If there is one.